Okay, so let us move on. The last family of density estimation techniques that I would discuss in this course are what are called as the non-parametric density estimates. Okay, we will look at that. A question to ponder upon: can you think of a map estimate for latent variable models? GMM with the Bayesian viewpoint, think about it. So we have GMM parameters, right? So what can we incorporate some belief on our GMM parameters, and can we get a map estimate for GMMs? That is a question to think about. Huh? Okay, so let us now look at the non-parametric density estimates. Okay, so far the way we have estimated density functions is by assuming that the underlying density function has a parametric form, and try to estimate the parameters via KL minimization, divergence minimization. That is what we have done. However, that is restricted by the fact that you start with some parametric assumption on the density function. Now what happens is, in some of the applications we may not need the entire functional form on the density function, but we only have to evaluate the density function at a particular point. Do you see the difference? The difference is, one, you estimate the entire density function and get a functional form, complete functional form. That is one way. So you assume the functional form a priori and you estimate the parameters. That is one way. That is what we have seen so far, right? Now there can be another way where you can only evaluate the density function at a given point but without knowing the entire functional form. Okay, in that case you need not make any assumption on the parametric family from which this density function is coming from. Okay, so though these methods that would not make any parametric assumption on the density function but only gives you a way to estimate the density function, evaluate the density function at a particular point, are the non-parametric density estimates. Okay, so let us look at some of those methods. These methods can evaluate the density function at a point without making any parametric functional assumption. See, for the case of the Bayes classifier that we are looking at now, this is enough. Why? Because finally remember that our Bayes classifier chooses based on P of y given x, right, and this we know is proportional to P of x given y times P of y, correct. If you can evaluate this P of x given y at the given x, that is all we need, no, we do not care about what the underlying functional form is. So we can use non-parametric density estimates for constructing a Bayes classifier, for instance. Okay, not always it is enough to have the density function evaluated. In some use cases you need the functional form as well, but there are cases where you do not need functional forms to be estimated, you only need them to be computed at a particular point, and non-parametric density estimates will help you do that. Okay, right. So now let us look at how to do this. Suppose Px is the density function that we are evaluating. Okay. And we say that x is in some RD, right, as usual. Let the capital R denote a region on the support of Px. Right. So, what is that? Depending upon what your RD is, a region can be a volume or it can be a hypervolume and so on. In general, it is a hypervolume. You see what I am saying? Suppose your density is supported on, let us say, one dimensional space, then by this region I mean a small line segment. If it is supported on 2 dimensions, this region is an area, and in RD it is a hypervolume. Okay. Okay, so let R denote that particular region on the support of Px. Now we need to compute, so let P be the probability of a point x falling within the region R. When you sample from this particular distribution, a point x may fall in region R or not, right. So now if capital P denotes the likelihood, I mean I should not be saying probability, it is the likelihood that this point is falling in this particular region, how do we compute that having this much of information? So this P is equal to, can somebody tell me? Yeah, it is the integral of the density function over the region R, correct? That is the definition, right? Right. Now let us keep it at one hand. On the other hand, let us say that we have n data points. So suppose we have n data points in our data set. We have n data points drawn from Px. So they are all drawn IID, okay. Now I can model, okay, the event of a data point, a particular xi falling in this region as a Bernoulli random variable. A data point x may fall in this region with some probability, may not fall in this region with 1 minus that probability, right. So I can model that as a Bernoulli random variable, right. Now I have drawn n of them, IID, right, it is a binomial distribution. So suppose I want to get an ML estimate for this Bernoulli random variable, which is the probability that this point x falls within this region R from this data, it is the ML estimate, the maximum likelihood estimate that I get for this particular Bernoulli random variable, right. Okay. Now if the event of a point, of a data point falling within the region R be modeled as a Bernoulli random variable, the ML estimate what is the ML estimate given? ML estimate for the parameter of that Bernoulli random variable is given by what is k here, can somebody guess? Is the k is the number of points within the region, correct? Okay. See, from our earlier analysis, we also know that this is equal to the integral of the density function over that region. We have written it here, right. So, this is equal to, from earlier, we know that this is equal to the integral of the density function right. Now, if r is small enough, then I can approximate this integral as the density function times V, where V is the volume of the region. I am making an assumption that within this region, right, that particular volume, the density function is a constant. Okay, that implies the estimate of the density function at that particular point is, the estimate of the density function at that particular point is now given by k upon n times V. So, this is the primitive estimate for the density in a non-parametric form. Actually, you have known this since your high school. Can somebody guess what is this? This is the histogram. So, suppose, how are you constructing histograms? Take a volume V, right, count the proportion of the volume, proportion of the samples that are falling in that particular volume, and that is the value of that histogram, and you assume that the density function is constant over that particular bin. This is exactly what your histogram estimate is. You remember constructing histograms, right? Yeah, that is exactly what it is. Now we have to extrapolate this idea into a d-dimensional space. So basically I am saying that the estimate of the density function at a given point x is given by k by n times V, where k is the number of times that your data point has fallen within a volume V, where V is a very small volume that is considered around that particular point x. See, this x, right, where this density function is being evaluated is the point around which you construct this particular volume, and you assume that within that volume the density function is a constant. Okay. Now let us extrapolate this idea into, formalize this idea and write it in a write it for the d-dimensional space. This is a non-parametric density estimate. Okay. So now here, right, we can actually do two things. One, choose a k, which means fix a k, and find what is the amount of volume that is needed to encompass these k points. The minimum volume that is needed to encompass those k points. That is one way to estimate the density. The other way to estimate the density is fix V, okay, and see how many points have fallen in that V. So that we will see both of the methods. See, one of the methods is called the Parzen window estimate, the other of the methods is called the nearest neighbor estimate. We will see that in a while. Okay. Now, two ways to do the above. Non-parametric density estimates. Like fix V and count k, or fix k and grow V. Okay, these are two ways to do it. Let us look at both the ways. So let us look at the first way, which is called the Parzen window estimate. Here we fix V and count K to estimate density, to evaluate density rather, not estimate. Okay. Now suppose we want to estimate, suppose we want to evaluate the density function at a point x. We are interested in evaluating the density function at a point x. Okay. Now what we have to do now, we have to first fix V, right, construct a volume around x. Now how do we construct a volume around x? Let R be a d-dimensional hypercube around x, centered around x, with length h. What is the volume of this? H power d, right? We are looking at a d-dimensional space and we have a hypercube of length h. Volume is h power d. Okay. Okay. Now what we should do is that, given that we have this hypercube, we will have to count the number of data points that are falling in this hypercube, right? How do we do this? So to count k, define a window function this sort. So call it phi of u is equal to 1 if uj is within half, j is 1 to d or 0 otherwise. It's just a unit hypercube, okay, centered around 0. Do you see this? This is a unit hypercube in a d-dimensional space centered around 0, right, with length 1. So that is what I am saying. So both the sides, if the magnitude is less than half, then it is counted as 1 or 0 otherwise. It is actually an indicator. So if a point is within this unit hypercube, then it is counted as 1 or 0 otherwise. Okay. Now if I have to extend this, right, to a hypercube, so if I compute, let us say phi of x minus xi divided by this particular h power d. So what does this function count? This function will count whether the point x, okay, is in the hypercube of volume h power d, which is centered around xi. Do you see this? If this is the definition of a unit hypercube, right, I mean this is actually an indicator. I mean this phi of u is an indicator that would tell whether a point is within the unit hypercube that is centered around origin. Now this one I am shifting the origin to xi and I am scaling the hypercube by h power d. So if you consider a cube of volume, hypercube of volume h power d around xi, this phi function will tell me whether a given point, or rather point x, is within this hypercube that is centered around xi. Does it make sense, right? Okay. Now remember that, so this, I will write that this is, so indicator or indicates whether x is within the hypercube of volume HD centered around xi. Okay. Now, do we have everything that we need to get the density? We do, right. So, remember that the density at x, a point x, is given by k upon nv, right. So, what is k? So, this will give you whether the point xi is within that particular, in fact I should have written it the other way around, right. So, this indicates whether xi is within the hypercube that is centered around x. See, it does not matter because it is symmetric, right, but still I will write it as xi is, I mean we will take x as our center because we are constructing the cube around x, right. So, it does not matter as long as you define your phi to be symmetric, the explanation is the same anyway. So, this is phi will give you whether the point xi is within this particular cube. So, this is for one data point. If I have to do it for k data points, what should I do? I will have to do a summation here, right. So, you just sum this over all data points. This is actually k. This will count how many data points within my data set have fallen around this hypercube that is centered around x. Okay. Then you divide this by n and that is it. So, this is the Parzen window estimate at x. Okay. In fact, this is exactly what your histogram is. If you take your d to be 1, this is histogram. Okay. Now, the indicator phi function that we chose here, right, this is very discontinuous in the sense that it's it's 1 only if it is within this. Why do not we make it smooth? In the sense that instead of hard counting, that is okay, if the point is within this cube I count it as 1, if it is outside of cube I count it as 0, I can make it smoother. What do I mean by this? I define, so phi of u can be made smoother by choosing phi of u to be so e power u minus some u naught. Instead of having hard bins, you can make your bins softer, right, by choosing your phi to be this. Now, if you make your function phi to be this, does not it look like a GMM? What you are actually doing is the density at a point x is now being estimated as a linear combination of multiple Gaussian functions raised around each of your data point. Do you see this? I mean, it is strictly not a GMM that way, but it looks like the density at a given point now is being estimated as a linear combination of multiple Gaussians that are constructed each around the data point. Okay. So, this is called the Parzen window estimate. I mean, this is a hyperparameter, okay, this is a user defined hyperparameter. You do not have to choose this to be this particular form, you can choose it to be anything, okay, and every choice that you make on this will impose a certain property on the final density estimate that you have. Actually, there is also a lot of literature around the convergence properties of these sorts of estimates. The question is, does this converge to the true density at a given point? So, at what sort of choices of, this is called the kernel function by the way, what choice of kernels does a Parzen window estimate converge to the true density estimate, and what should be the minimum n that should be chosen? You can construct bounds on it and so on, which I will not discuss in this course. Does it make sense? So, now come again. So, I am saying you can choose this kernel to be anything, it need not be the hard bin that you have constructed, you can make it to be a smoother function. Depending upon what choice that you make, the estimate will change, density estimate will change. And please note, there is one other important thing that is to be noted here is that this changes at every x. See, unlike the parametric density where once you have data you estimate your parameters, this get fixed. So this changes for each x. So that is why this is a non-parametric estimate. So every time you make a decision, let us say that you use this for your class conditional density and constructing a base classifier. So for every data point this has to be computed every time. You see this? So a sum over all data points have to be computed every time that you estimate the density. Unlike in the parametric case where you estimate it once and keep it. That's why I told you, right, in non-parametric density estimate case you estimate, I mean you evaluate the density without estimating the final functional form, that is the idea. But every x you have to do it, you have to compute this again, you have to compute this kernel for every x, every new x you will have to compute this. In non-parametric density estimate, in parametric density estimate what happens, you assume that to be, let us say, a Gaussian, you get the mean and the variance using the data, you fix it. You still have to evaluate, but the thing is you do not have to compute the sum every time that you do it. That is in that way this is computationally heavier. I mean that is constant time, this is linear time, linear in terms of number of data points. Okay. So this is okay.
For this exponential form, it's not really sort of an indicator of count.
It is not the indicator of the count. Yeah, it is. Yeah, it is. Okay, that's a good observation. In the if you make the kernel to be this Gaussian kernel, right? It's not counting how many points are within that particular hypercube. It is counting in a soft way, you can say. No? It's not the hard counting; it's the soft count.
That point is everywhere with some probability.
Okay, so let's look at the other case. The first case was where we fixed v and yeah.
So why are they not exactly equal to the GMs if you put in that way?
Okay, the question is why is this not exactly a GMM? It's not exactly a GMM because in a GMM the Gaussians that you construct, the parameters of that Gaussians is not these, are not these. You estimate them using the data. Here they're simply Gaussians with fixed parameters that have been defined, that's it. Looks like Gaussian, that's what I said. It looks like a GMM but it's not a GMM in the strictest sense. Yeah.
The phi function, it should be divided by h, right? Not by h power d.
Where?
The phi function.
Here. This is v, no? This is kn by v.
Phi function. You have written as x, you have written as phi of x minus xi by h power d. Shouldn't it be divided by h?
Should it be h or hd? Let me just yeah, correct, that's correct. Thanks for the correction. This is not because for this is you are doing it for each dimensions, so it's like you shift it and scale it with h. Yeah, that's correct. So h power d appears here in v, not here. Correct. Thanks for that correction. Do you all see what he said? You take that indicator function, you shift it and scale it with h, where h is the length of that hypercube. No, you don't divide it by, you don't scale it with h power d, you just scale it with h. It's correct. Okay, we will stop here and continue in the next lecture.